Welcome to the fourth lecture of the module on astrophysics of neutron stars. In this lecture, we would talk about magnetic fields. Now, the magnetic field is one of the most important parameters of a neutron star. It not only controls the physical processes that take place in the magnetosphere outside the neutron star, it also affects many processes inside the neutron star, and the evolution of magnetic fields basically determine the overall evolution of neutron stars with time. Now, before talking about the magnetic fields themselves, we would be looking at the transport properties of neutron stars, because transport properties, thermal conductivity, electrical conductivity, they determine the nature and the behavior of magnetic fields inside a neutron star. So, this is a plot of the electrical conductivity with respect to density, and these plots are made for different models for different values of temperature. The important thing to note is the sharp rise in conductivity with density, and also the fact that we do not really worry too much about the electrical conductivity inside the core of a neutron star. The plot goes up to about 10 to the power 14 grams per cc, that is definitely the core density, but we would only be discussing and worrying about the transport properties in the crust, because in the core, if the material is superconducting, that is the protons are in a superconducting state, then the magnetic field is supported by superconducting flux tubes, and such a magnetic field does not evolve with time. On the other hand, if the core is not superconducting, even then the electrical conductivities are so large that magnetic field does not really evolve with time. We would discuss more about it in the later part of this talk. So, we are basically concerned with the transport properties in the crustal region of a neutron star. Now, here is a similar plot of electrical conductivities, but here some impurity has been included. So, for example, look at this plot number 7. This is a plot without any impurity, and this is the corresponding plot with a impurity concentration of 0.2. Now, what is impurity? We expect the crust of a neutron star to be composed of beta catalyzed matter in its equilibrium composition. How do we obtain that? For a particular density, we minimize the energy corresponding to various nucleonic species, and whichever species minimizes the energy is the most favored species, nucleonic species at that density. However, if the neutron star is undergoing accretion or have undergone accretion sometime in the past, the crustal composition changes from this beta catalyzed matter. How, we will see later. So, when that happens, there are different kinds of nucleonic species, perhaps intermingled at a particular density. Also, there might be defects, there might be dislocation in the crust, all of which would affect the conductivity. And for want of better knowledge about these parameters which might affect the transport properties, we put them together in this parameter called impurity consideration and use the value of conductivity that is obtained from there. Now, not only in the accreted crust, but also in a neutron star which has not undergone any phase of accretion, there might be small amount of impurity, there might be defects and dislocations. So, in isolated neutron stars which has not undergone any phase of accretion, also electrical conductivity might be affected by such impurities. This is a plot for thermal conductivity, and this plot has been made for various different kinds of material in the outer crust near the envelope region at a temperature of 10 million Kelvin, and you again see sharp rise in the conductivity, thermal conductivity this time with density. Now, this is a cross section of an accreting neutron star. If the temperatures are large enough, there might be hydrogen burning shell, and immediately beneath that there would be a region of helium, and then of course, there would be regions of iron from a density of 10 to the power 7 grams per cc, and beyond that we would have the solid crustal region within which there might be some heat sources because of certain processes undergoing in the accreting crust. Now, one has to remember that this region where hydrogen burning etc. is going on are very shallow. You see the numbers here, it is between 50 centimeter and 80 centimeter. Now, these numbers may not be very accurate, it would depend very much on the equation of state etc., but these numbers tells you the length scales over which processes in neutron stars happen. Within a few centimeters things change and determine the overall evolutionary behavior of the magnetic field as well as the neutron star itself. Now, this is a thermal profile, the temperature profile of a heated crust, accretion heated crust. This is showing temperature as a function of density, and you see that the temperature rises very sharply from the envelope region and then stabilizes for over the entirety of the crustal region. But this happens only if there are no impurities present. As we have discussed, there will be large amount of impurities present in an accreting crust, and if that is taken into account, then we have a temperature inversion. In this case, temperature inversion means that crustal region has higher temperature compared to the core region here. So, the temperature undergoes a maxima in the outer region at a densities of 10 to the power 6, 7 grams per cc, and then drops again towards the interior. Now, this kind of inverted temperature profile affects the magnetic field strongly and therefore changes the long time scale behavior of a neutron star. This is a diagram showing the various nucleonic composition in an accreted crust. So, you see that the value of Z, that is the atomic number of the preferred nucleonic species, changes very much. These different colors are for different values of the atomic mass number, as has been shown here, and one can see that this is very different from a neutron star in which you would expect beta catalyzed matter. Now, let us talk about the magnetic field itself. Now, this is our familiar dipole field configuration of a neutron star. There is a dipole field at an angle with the rotation axis of the neutron star. Now, one must remember that the magnetic field and the rotation axis has an angle which varies from neutron star to neutron star. This angle, known as the inclination angle, could even be 0, that is, the rotation axis and the magnetic axis could be aligned, or it could be 90 degree, completely misaligned, orthogonal to each other. So, here we see a standard picture where the inclination angle is between 0 and 90, and we see that there is a light cylinder within which the closed field lines are there, and particles are being accelerated along the open field lines. Now, that is the outer picture of a magnetic field. How does the field lines look like? What is the internal configuration of such a dipolar field? If it is a star centered dipole, the magnetic flux threading through the entirety of the neutron star, then it would look somewhat like this. This is the boundary of the neutron star, this is the boundary, and magnetic field lines are going through the star in this fashion. On the other hand, we have said that the interior of the neutron star has a proton superconducting component. If that is so, then it is possible that there is total flux expulsion and the magnetic field is entirely supported by currents in the crust. In that case, the internal configuration of the magnetic field would be like this. It would thread the crustal region, outside it would be matched to a dipolar field, but there will be no flux, no magnetic field lines inside the core region. Now, that is not all. We have so far talked only about dipolar fields, but there are indications that the neutron star field may not be purely dipolar. Now, the pulsar emission itself requires very small radius of curvature near the neutron star, which essentially means higher multipolar components must be present, and on the other hand there exist very slow pulsars. The maximum spin period of a radio pulsar that has been measured is 23.5 second. Now, for such slow pulsars to remain active as radio pulsars, very strong, very twisted fields and very strong higher multipolar components near the surface are required. Now, this is a schematic diagram showing higher multipolar components present along with the large scale dipolar field. There are also indications from magnetar activity that the field may not be purely dipolar. There are also some observational indications. This is a picture which shows the surface footprints of the field, and this might be indicative of smaller structures that exist in the magnetic field. Now, let us see what kind of magnetic fields we are talking about the strength. Now, we can measure the magnetic field in many ways. We can measure the magnetic field from the secular spin down of pulsars, and the magnetic field is proportional to the square root of period and period derivative. But I want us to remember this is only the dipolar component of the field that we are measuring. We do not have a handle on multipolar components even if they are present. Now, in accreting neutron stars, if there is channelized accretion and if we can measure the rate of accretion, that is m dot, by some other observation from some other parameters, then we can have an estimate of the magnetic field, the dipolar component of the field at Alfvén radius. Now, Alfvén radius is that radius at which the magnetic field pressure equals the ram pressure of the particles incoming and accreting onto the neutron star. On the other hand, for certain neutron stars, cyclotron lines have been observed. If you can measure the strength of the cyclotron line, from there we can get a handle on the field strength of the magnetic field from the region where the cyclotron line is being produced. But obviously, there are a lot of uncertainties, because what we are measuring primarily is large scale dipolar field, which is coming from radio pulsars, which comprise the majority of observed neutron stars. We also do not have any understanding of multipolar structures near the surface and no knowledge of the field structure in its entirety. If we want to talk about the origin of the magnetic field, from where did such strong field came about, we have to admit at the very beginning that we really do not have any consensus on this issue. The magnetic field can be generated in the core, or it may have been generated in the crust. Firstly, it could be a fossil field, that is, the progenitor of the neutron star had in its core some magnetic field. At the time of collapse to a neutron star, if the flux has been conserved, then a simple scaling which goes by the radius of the progenitor divided by the radius of the neutron star square, then the scale factor is large enough to give us the strength of magnetic field that we observe in today's neutron stars. Or perhaps the core got spontaneously magnetized to the state that we see today, or it is possible that from a seed field this immensely strong magnetic field has been generated by turbulent dynamo amplification in the proto-neutron star phase. Now, one has to remember that all of these propositions have certain problems, and it is not yet clear which of these propositions, or if any of these propositions, is the real reason for generation of the magnetic field that we see. Now, the magnetic field could also be generated in the crust by running a thermoelectric battery or a dynamo from a seed field in the very early phase of the neutron star, when the crust was in a liquid phase. Of course, after the crust becomes solid, then such processes cannot run there. Or the poloidal field may have been generated by having strong toroidal field component in deeper regions of the crust. The problem with generating field in the crust is, then we do not know how the magnetic field in the core region has been generated. That problem remains, and many indirect observational indications are forcing us to believe that the magnetic field cannot be entirely confined to the crust. It must have a component in the core, and therefore, the major issue remains that of generating the magnetic field in the core of a neutron star. Depending on the generation scenario, the magnetic field could be located in different parts of the neutron star, either in the superconductor as superconducting flux tubes, as we have seen and discussed before. There would be huge number of fluxoids to support the observed neutron star magnetic fields, or it could be supported by currents in the crust, or if the core is not in a superconducting state, it could be supported by charged particle currents in the neutron proton electron plasma in the core. Whatever may be the location of the magnetic field, one has to remember that the actual dissipation of the magnetic field happens only in the metallic crust, and this happens because magnetic field cannot be dissipated or changed if it is supported by superconducting flux tubes. If the core is not superconducting, even then the conductivities are so large that magnetic field would not evolve even over Hubble time scale. So, therefore, if we are talking about magnetic field evolution, we have to have magnetic field residing in the crust or brought to the crust by some mechanism. Finally, let us talk about the evolution of magnetic fields. Now, the time evolution of the magnetic field is basically governed by this equation known as the induction equation, and there are mainly two terms. This is the transport term. This contains the velocity of the charged particles, and it transports the flux from one region to another, and this is the ohmic dissipation term. Because of the conductivity, magnetic field is dissipated. Now, this equation has been written for a single component charge species. If we have more than one charge species, then the equation would be modified to accommodate for more than one charge species. Now, what is important in this equation is the conductivity. This is the electrical conductivity, which depends on a number of parameters. Sigma depends on density, as we have already seen. It depends on the equilibrium nuclide at that density. It depends very strongly on temperature. With increasing temperature, there is possibility of larger number of collisions amongst the charge carriers, that is the electrons, and therefore, at higher temperature electrical conductivity decreases, and it also depends on the impurity coefficient, as we have seen before. The time scale of this ohmic dissipation is given by a quantity which is proportional to the electrical conductivity and proportional to the square of the length scale over which the currents supporting the magnetic field are spread. So, that determines the time scale of the magnetic field. Early in the history of neutron star astrophysics, it was shown that the value of electrical conductivity in an ordinary neutron star, which is not accreting material from its companion, is such that even if the magnetic field resides in the crustal region, the time required for the magnetic field to evolve, to undergo any kind of change, is larger than the Hubble time scale. So, therefore, magnetic field dissipation is very small in isolated neutron star, except under certain conditions, certain special conditions, and we would see what happens in other situations. For isolated neutron star, even if the conductivity is lowered by having a large amount of impurity and therefore, having a shorter dissipation time scale, if the magnetic field is residing in the core, there cannot be any evolution of the magnetic field. Now, we know that isolated neutron stars, because of its radiation, undergoes spin down. So, the spin down of a neutron star would necessitate expulsion of rotational vortices from the core region, because the rotation of neutron star is mainly supported by the rotational vortices in the neutron superfluid, and we have already said that the neutron superfluids are intimately linked through nuclear interaction, the strong force, to the magnetic fluxoids that are there in the core. So, when rotational vortices are expelled because of spin down, because of interpinning of the rotational vortices and magnetic fluxoids, we expect that magnetic fluxoids are also expelled to the metallic crust. Now, once the flux has been expelled to the metallic crust, it gets deposited at the core crust boundary and it can undergo ohmic dissipation. and there might also be Hall transport and ambipolar diffusion in the metallic crust. So, therefore, spin down induced flux expulsion and subsequent field evolution is a possibility of changing the magnetic field of isolated neutron stars. Now, in this context, what is very important is not the ordinary isolated neutron stars, where the amount of field evolution is not significant to change the nature of such an ordinary neutron star, but it might be important for neutron stars which are undergoing repeated glitches. Now, in the previous lecture we discussed about glitch and we hinted at glitch induced field evolution. So, if there are repeated glitches, there might be increased magnetic stresses generated at the core crust boundary. There could be very large crust cracking, and this may induce expulsion of a large number of magnetic fluxoids. So, instead of a secular spin down and a slow expulsion of magnetic fluxoids, with glitches there might be expulsion of large amount of magnetic fluxoids at one go. And if a pulsar is a repeated glitches, then there might be significant expulsion of the core flux and dissipation of such core flux in the crust may change the nature of the neutron star. This is a picture of how ohmic dissipation may affect the magnetic field in an isolated neutron star, and the top curve is for a dipolar field, and it is seen that even for 10 to the power 8 years the decay is not much. What happens for higher multipoles, that is very interesting. If there are higher multipoles in the neutron star, they decay much faster than a dipolar magnetic field, and higher the multipole, the quicker they dissipate. As you can see, this is for multipole of 8th order, this is for 25th order, and this is for the 45th order. So, even if a neutron star begins with large multipolar component, we see that they would dissipate away very quickly. But we have said that multipolar components are required over long time scale, and there are also observational indications of such multipolar components. So, something else might be happening which we will discuss now. Before that, let us talk about the accreting neutron stars. In accreting neutron star, what can happen is, as long as the neutron star does not have physical contact, that is, it does not have active accretion onto its surface, it is undergoing secular spin down, and there could be spin down induced flux expulsion. After that, it would be followed by ohmic dissipation. Now, the interesting part of an accreting neutron star is, as we have seen, the temperature would be raised, and therefore, there will be enhanced ohmic dissipation in the accretion heated crust. Now, that is one of the major mechanisms of actual decay of the magnetic field strength. There could also be diamagnetic screening, the burial of the magnetic field because charged particles are being accreted, but it has been seen that such screening may not be long lived, and once the accretion process stops, the field would re-emerge. There could also be processes of burial of the magnetic field through fallback hypercritical accretion that happens in a newly born neutron star. It may accrete from the supernova remnant, and that accretion may be hypercritical and the field really gets buried, and one expects that this field would also re-emerge over a time scale, and the newly observed neutron stars of the class central compact object or CCO, these are objects which are sitting at the center of supernovae, but they are not acting as pulsars. The conjecture is because of such hypercritical accretion, their magnetic field has been buried. Over time, this field would re-emerge or emerge, so to speak, and when that happens, they would function as normal radio pulsars. Now, we were talking about multipolar fields. Now, a magnetic field we have so far considered have been purely poloidal. Even when we considered higher multipoles, we kept the magnetic field purely poloidal. What happens in reality might be different. The magnetic field may have also a toroidal component. Now, when that happens, then we have these two equations for the evolution of the poloidal component and the toroidal component, and we immediately see that there are mixing of components. So, when a toroidal field is present, different multipole components would not evolve independently as we have seen in the plot before. Rather, they would get intermixed and the evolution would be far more complicated than the simple case that we have considered before. In presence of a Hall term, more than one charged particle species present, there would also be multiple mixing. So, therefore, depending on the initial configuration of the magnetic field, the evolution would be determined by the transport properties as well as the initial condition of the field. And a lot of work is being done in this direction, particularly in the context of magnetars, which are neutron stars with very strong magnetic field of the order of 10 to the power 14 to 10 to the power 15 Gauss, and it is believed that in magnetars such complicated initial conditions are realized and the evolution of magnetic field is also consequently very complex there. Now, in an accreting neutron star, if the magnetic field is strong, to channelize the incoming material, then the accretion happens through the polar cap. The material accumulation happens at the polar cap, and this material is confined by the magnetic stresses, and the material remains accumulated on the polar cap, forming a mountain on the polar cap as long as the pressure of this column does not become larger than the pressure of the magnetic field, which is sustaining this pressure. But what is the result of such a magnetic confinement? The material flows only from the bottom of such a column. So, the material would basically flow sideways and reach equator, where material from the other pole would also arrive and meet at the equator, and then it would slowly backtrack, and finally, in the deeper layers of the star, what would happen would be a radial inward compression of the entire star. Now, this is a very schematic description of the material flow in a neutron star, and as you can see that the dimensions are all wrong. The crust has been shown as much thicker than the dimension of the core. This is simply to describe the nature of the material velocity. The magnetic field would also get extremely distorted. This is a picture from a work by Payne and Melatos, slightly old, and as the material flows, the magnetic field gets distorted. And when magnetic field gets distorted like this, there is probability that the magnetic fields would form small loops and get dissipated very quickly. So, the outlook of field evolution is there are multipolar field configurations that one needs to consider, and one has to consider the presence of toroidal fields, the physics of magnetars, which is very important in present time, requires understanding such field configurations, and one also needs to understand how higher multipoles and toroidal fields evolve through the flow of accretion material. And what happens to the final field structure through such process would be obtained from various observational indications.